Yeah, thank you very much, Vitor. I mean, this has been a great meeting for me. I've learned a lot. I hope other people have learned a lot. I've met a lot of people. I met a guy in the lobby of the hotel who was a big Georgia Bulldog fan. So, you know, that's always bad these days if you're a Florida Gator fan. But he was telling me how he just getting the same joy from watching the Bulldogs play as he used to because he wasn't feeling that well. He had a lot of illnesses, and he just didn't get the same thrill out of seeing Georgia kick the living hell out of whoever they were playing this week. So he went to the doctor, and he told the doctor all his symptoms, and he said, you know, I just don't know what's wrong with me. And the doctor said, don't worry, we'll do some tests. I'll take a blood test. Maybe we'll do a CAT scan. We'll figure out what's wrong. So about a month later, he got a call to come in and get the results of the tests. And the doctor said, well, I have good news, I have bad news. And he goes, oh, well, give me first. And the doctor says, well, we're going to name a new disease after you. The bad news is there's no cure. So that's how I wanted to organize my talk about effects of heat stress and reproduction. The good news, bad news. But I'm going to start with the bad news first and then talk about the good news. And I define heat stress as something outside the cow that affects the cow's physiology. You know, of all the organisms in the world, there's only two classes of organisms that try to regulate their body temperature, birds and mammals. So they invest a lot of resources to try to keep their body temperature at a constant and high level. So birds do it, mammals do it. Every other life form on Earth lets its body temperature vary with the air temperature. So heat stress, I define as the sum of all the forces external to the animal, the air temperature, the wind speed, the solar radiation, the humidity, that act on the animal to make it difficult to regulate its body temperature. So that's heat stress. And many times animals experience heat stress, but they can modify their physiology so that they keep their body temperature constant. And there's very little consequences for heat stress on the animal. But when heat stress is so severe that the animal cannot lose all of the heat it produces from metabolism to the surrounding environment, its body temperature goes up. And that increase in body temperature has a lot of consequences for reproduction. Embryo mortality is high when body temperature is high. The oocyte is killed by high body temperature. The sperm is damaged by high body temperature. So the magnitude of increase in the cow's body temperature during heat stress is related to how bad the cow's reproduction is. And of course, there's genes that affect how the cow can respond to heat stress. Right? The cow's probably got about 25,000 genes that control everything in her body. And some of those genes make it more difficult for the cow to regulate her body temperature. And some of the genes make it easier for the cow to regulate its body temperature. So the first piece of bad news I have is that heat stress affects most aspects of reproduction in both the bull and in the female. And the magnitude of the effects of heat stress are related to how high the cow's body temperature or how high the bull's body temperature is during heat stress. So on the cow side, heat stress affects estrus behavior. Heat stress cows express estrus for a shorter period of time and they don't mount as often per hour during estrus as non-heat stress animals. And probably the biggest effect of heat stress is on fertility, that the oocyte is damaged by heat stress, the very early embryo cannot survive in a high uterine temperature environment, and so fertility can be reduced during periods of heat stress. On the bull side, the bull is just like the cow. High elevated temperature damages spermatogenesis at the earliest stages of spermatogenesis. So sperm production goes down, sperm quality goes down during periods of heat stress. And Philippe Morial talked about this yesterday. For a long time, we didn't really think about what heat stress does to the pregnant animal or to the fetus inside that pregnant animal. But now we know that elevated body temperature in a pregnant cow can compromise how the fetus grows, and that has effects maybe throughout the life of that animal. Certainly in dairy cattle, milk yield is compromised permanently if that cow was heat stressed while it was just a fetus. So a lot of severe effects of heat stress potentially on reproductive function. These are some data from dairy cows. There's a lot more data on dairy cattle than beef cattle, so when I couldn't find any data on beef cows, I just used some dairy cow data. There's some data from Arizona just showing the length of estrus in the cool period of the year versus the long period of the year. You can see estrus duration goes down, the number of mounts goes down. And here's some data from a commercial dairy in Florida looking at the estimated number of missed heats. You know, how many cows were in heat and nobody noticed? So it was never very good, right? More than half of the heats are not detected by the herdsman. But during the summer, when estrus expression goes down, the number of missed heats goes up. You can avoid the effects of heat stress on estrus detection by doing fixed time AI, not include estrus detection in the equation. But the other problem is the likelihood that an insemination, either from a bull or by artificial insemination, will result in pregnancy can be reduced by heat stress. This is a paper, probably the first paper ever published on heat stress in beef cattle at Louisiana State University in 1971. They synchronized estrus in a bunch of Hereford heifers. As soon as the heifers were in heat, they artificial inseminated them and then trucked them to an environmental chamber. One chamber was kept at 90 degrees Fahrenheit, 65% relative humidity. The other chamber was kept at 70 degrees Fahrenheit, 65% relative humidity. And here are the pregnancy rates, which I have backwards. Sorry about that. So just trying to make sure you're all paying attention. If the animals were kept at 70 degrees Fahrenheit, 48% became pregnant. But if they were at 90 degrees Fahrenheit for just 3 days, and they weren't heat stressed until after they were bred, none of the animals got pregnant. The magnitude of heat stress effects depends on the ability of the cow to regulate its body temperature. So 2 animals could be exposed to the same air temperature, same relative humidity, same solar radiation, but the cow that can regulate its body temperature is going to be less affected by heat stress than the animal that's not. Here's some more dairy cow data showing seasonal variation in conception rate for lactating dairy cows. You can see this big drop in conception rate during the summer. And then for non-lactating heifers. So in the heifer, this is in Florida. This is about as hot as it gets. No drop in pregnancy rate in the summer because the heifer can regulate her body temperature. But the lactating cow, her heat production has probably tripled because she's lactating. And it's not possible for her to maintain her body temperature in the summer, and so fertility goes down. Neil Schrick was talking about fescue in glowing terms yesterday. Fescue affects ability of animals to regulate their body temperature. So here's some data from Arkansas. If cattle are not on fescue or endophyte-rich pastures, the calving rate was 80% in the animals bred in August, so hot time of the year, and 100% for animals bred in February, the cool time of the year. So there was a reduction in pregnancy rate, but not by very much. But if animals were in endophyte-rich pastures, you can see the effects of heat stress are greatly magnified. Again, in the winter, when the animals can regulate their body temperature, no difference in pregnancy rate based on the level of endophyte in the pasture. But in the summer, big drop in pregnancy rate. Animals fed fescue, like Neil said, have big hairy hair coats, have a difficult time regulating their body temperature during heat stress. So, what is the body temperature that starts to cause a reduction in fertility? It's hard to say because it's hard to do an experiment to find that number. And, maybe it's not just the magnitude of how high the body temperature is, but some combination of how high the body temperature is and how long hyperthermia takes place. But just from myself looking at all the data, so you can take this with a grain of salt, probably when body temperatures go up about 1 degree Fahrenheit, so normal body temperature in a cow, somewhere between 101.3, 101.5 degrees Fahrenheit. If it goes up above 102.2, I think you start to see a reduction in fertility. So one thing we'd like to do is keep animals from spending much of their day in an environment where they can't regulate their body temperature. So the second piece of bad news is the effects of heat stress can persist long after the heat stress is gone. It's not like you can cool the cows on the day of AI and you've reduced the effects of heat stress. They were heat stressed 10 days earlier, 20 days earlier, 40 days earlier, and that's going to affect their fertility. And the reason for that is that it takes a long time for a sperm cell to mature. It takes about 60 days from the primordial spermatogonia to the fully mature sperm. Takes about 60 days. In the female, we're not exactly sure how long it takes an oocyte to develop, but at least 90 days, maybe 120 days. And heat stress during those early periods of gamete formation can affect the fully formed gamete several weeks later. So here's some data from Oklahoma where they kept bulls in a cool environment or a heat stress environment for 8 weeks. You can see the number of motile, or the percent of motile sperm go down in the bulls that are heat stressed. And then they removed the heat stress. But it took another 8 weeks before the percent motile sperm had returned to normal. Until the last sperm that was spermatogonia when heat stress was taking place had been removed from the testis. And this is true in the cow as well. So a cow that's in heat today, that follicle probably started growing 3 or 4 months earlier. So anything that happens in the life of that cow that affects the ovary could potentially affect that cow's fertility. That's kind of a sobering thing to think about. And it's been shown that heat stress, as early as like 120 days before estrus, can affect how good this oocyte is in getting fertilized. And then after the embryo is formed, the very early embryo is very sensitive to heat stress. But after about 3 days of pregnancy, so 72 hours after ovulation, that embryo becomes resistant to heat stress. So if you heat stress a cow at day 5 after breeding, day 7 after breeding, doesn't have much effect on fertility. Heat stressor 1 day after breeding, yes. So here's results from an experiment in Brazil using gyr cows, so pretty heat-tolerant cows. What they did in this experiment was either keep cows in cool conditions continuously, or they exposed them to heat stress for just 28 days. And then they collected oocytes using oocyte pickup periodically in the control cows and in the heat stress cows, and then measured the ability of those oocytes to get fertilized, produce embryos. And so you can see after heat stress, there's a decline in the ability of those oocytes to become embryos, and that decline lasts to 133 days of the experiment, so 103 days after the experiment ended. The oocytes still had not recovered when compared to the control oocytes. So that's bad news. So I have 3 pieces of good news. And the first piece of good news is that beef cattle are much less likely to be affected by heat stress with respect to reproduction than dairy cattle. Why is that? Well, they produce a lot less metabolic heat than dairy cattle. And most of the research on heat stress has been with dairy cattle. So even a lactating beef cow is not producing nearly as much heat as a lactating dairy cow. And then, unlike dairy cows, which at least in the US are bred every week of the year, beef cattle are not usually bred at the highest time of the year. So they avoid some of the negative effects of heat stress on estrus and fertility just because they're not being bred at that time. The fetus will still be susceptible to compromise, but effects on estrus behavior, on bull fertility, will be minimized just because we're not breeding cows the hottest time of the year. And then many breeds are thermally adapted, have genes that make them regulate their body temperature better. So I've spent a lot of time looking in the literature for data showing a reduction in reproductive function of beef cows under practical conditions due to heat stress. And it's really hard to find those papers. Most papers, I mean, there are a few papers to begin with, but most of them compare reproductive function in fall breeding seasons versus spring breeding seasons. So for example, here's some data from Oklahoma comparing calving interval in a spring calving herd. So the cows are getting bred May, June, July, so very hot time of the year, with a fall calving herd in red, where the cows are getting bred January, February, March in Oklahoma. And you can see there's really no difference in calving interval. There's a whole bunch of genetic groups here. Hereford Angus, Angus Hereford crosses, not thermal tolerant. And then all these other groups have Brahman in them. Brahman Hereford Angus, Brahman Angus Hereford, etc. But even if you just look at the Boss Taurus breeds, No real evidence that fertility is being compromised in the spring calving group. And here's some more data from this same paper, just looking at the calf crop. No difference in calf crop between spring and fall breeding herds. Here's some other data from Clay Center, Nebraska. This is over 10 years worth of data comparing what percentage of cows are pregnant at pregnancy diagnosis, what percentage of cows actually calve for animals with a spring breeding season, so May through August, versus a fall breeding season, October through December. So this is in Nebraska, again, where it's hot in the summer. And you can see there's no difference in the heifers in pregnancy rate, at pregnancy diagnosis, or calving rate, and the same is true for in the cows. So beef cows are pretty resistant, or I shouldn't say, are less likely to be affected by heat stress than dairy cows. So the second piece of good news I have is there are genetic solutions to the problems of heat stress in beef cattle. There are thermal tolerant breeds like this Brahman cow, which has got a whole host of genes, not probably just one gene. She's got a bunch of genes that make her regulate her body temperature better than a Bos Taurus. And actually, even her cells respond differently to elevated temperature than a Bos Taurus. So like we've taken Brahman embryos, exposed them in the lab to high temperature. They're less likely to be blocked in development than if we take an Angus or a Holstein embryo. So there are lots of genes in this breed, and then there are other breeds as well that make them resistant to heat stress. And of course, these breeds are thermal tolerant because of individual genes. If we could identify those individual genes, we could transfer those genes into Bos Taurus cattle without transferring all the genes that maybe we wouldn't really like to see, like the temperament genes or poor tenderness genes. So let me just show you some data. I'm very impressed with the Brahman in terms of its ability to regulate its body temperature during heat stress. We did an experiment a few years ago where we worked at the multi-breed herd at the University of Florida that Thiago Martins was talking about yesterday. So we have cattle from 100% Brahman to 100% Angus by increments of 3%. And we put a blank cedar, no progesterone, that had a temperature recording device attached to it in the vagina. So we could measure vaginal temperature every 5 minutes for 7 days. And then we put radio collars on them so we could see where the cows went. So here was the chute, then they go down the lane, and they spend the week in this pasture. So we could study their body temperatures, study their behavior. So this graph shows the vaginal temperature during the hottest time of the day, so between 3 p.m. and 7 p.m. That's when body temperatures peak. And I did actually have degrees Fahrenheit here, but it's disappeared. Anything above 39 would be considered a temperature that might affect fertility. And we measured this in 2 weeks, just by chance. 1 week, period 1, was a lot hotter in terms of air temperatures than period 2. So if you look at period 2, where it's not as hot, the Brahman animals regulated their body temperature the best, no real increase in body temperature. The 6/8 Brahman regulated their body temperature very well. 50% Brahman, I think most people would consider that a very well-adapted breed. but it still has higher body temperature than the Brahman, though less than, say, the Angus or quarter Brahman. But as you decrease the percent of Brahman, body temperature goes up. In the week that was hotter, all the animals have higher body temperatures. And the only breed group that was different was the 100% Brahman. So even an animal that was 25% Brahman didn't regulate its body temperature much differently than an Angus. Then we also looked at their shade-seeking behavior. So one thing I've always noticed driving by herds of cattle that have Brahmins and non-Brahmins is you can never see the non-Brahmins because they're in the woods, but the Brahmins are out grazing. So we looked at what percent of time do these cows with radial collars spend near the tree line. We couldn't tell whether they were in the trees or just near the tree line. So you can see in the morning, they're all grazing. None of them are near the trees. And then as it warms up, most of the animals spend about half their time in the shade, but not the Brahmins, right? They still remain out in the pasture doing whatever, but spending a lot of their time presumably grazing. And even the 2/8 animals are less likely to seek shade. So Brahmins and other thermal tolerant breeds, Bos indicus breeds, are very thermal tolerant. But you don't just get the thermal tolerant genes with the Brahmin, you get all the genes. And Thiago showed these data yesterday. Brahmins have problems, right? They're very slow to reach puberty. And as I'll show you in this slide, which is Thiago's, their pregnancy rate to fixed time artificial insemination, at least at the University of Florida multi-breed herd, is lower. So animals that were 100% Angus, pregnancy per AI was 57%. For animals that were Brahmin or nearly all Brahmin, it was just 37%. This is almost a linear decrease in pregnancy per AI as the percent Brahmin goes up. The calf crop was the same. The number pregnant at the end of the breeding season was the same, but they responded poor to timed AI. Brahmins don't respond the same to some of the hormones used for timed AI. Some of them are probably stressed going through the chute, which affects their response to the hormones. So even though they're more resistant to heat stress, their fertility is not necessarily higher than animals that are less sensitive to heat stress. There are other breeds. There's lots of thermal tolerant breeds in the cattle world. The USDA at Brooksville used to examine alternative breeds to the Brahmin for thermal tolerance. These are some of their data. So these cows were run through a chute. So just running them through the chute probably increased their body temperature. And they did this in August, and they did this in December. So in August, when heat stress is an issue, you can see that the Angus and the Hereford have higher body temperatures than the other breeds, which were Brahmin, Senepol, a interesting breed from St. Croix, the Virgin Islands, probably 11% Bos indicus, and then crosses between Hereford and Senepol and Hereford, and then the Romo Sinuano. Probably none of you have Romo Sinuano in your herds. A Criollo breed from Colombia, kind of like the Longhorn. Much better at regulating their body temperature than Hereford or Angus. Also probably don't grow as much. And then you can see in December, when heat stress is not an issue, the animals with the highest body temperature were the Brahmins, probably because they were getting stressed out running through the chute. One of the things we're trying to do is find the specific genes that make a Romo sinuano or a Senepol or a Brahmin more resistant to heat stress, and then put those specific genes in breeds of cattle that are more productive. And the first example of that was really started by a guy named Tim Olson at the University of Florida. And Tim was looking at crosses between Senepol and Holstein, and he noticed, hey, some of those cattle have really short hair coats, but some of those cattle have kind of normal hair coats. And when he looked at it some more, he realized this slick hair coat, he called it, is a dominant trait. And so he started studying this gene. Eventually, we found out that this mutation is caused by a mutation in the prolactin receptor gene. So prolactin, hormone that causes lactation, also inhibits hair growth. So in the summer, cattle have short hair coats because prolactin is high. And then in the winter, prolactin's low, they have shaggy hair coats. Fescue reduces prolactin, get hairier cattle. So we don't understand completely, but we think this prolactin receptor mutation is making prolactin more effective. So hair coat is inhibited more than it would be ordinarily in the summer. So Tim, and then when Tim retired, I started studying these animals. So we've actually put this slick mutation into Holsteins. So here is a normal-looking Holstein, and here is a Holstein. She's essentially 100% Holstein, but she's descended from a Senepol cross in the 1980s. And you can see, maybe not very well, there's very little hair on the pole. Here's another slick animal. You can actually see the wrinkles on the face because the hair coat is really short. And we trimmed a piece of hair from the flank of a slick cow and a wild type cow. This is in the summer, so the wild type cow's got a short hair coat, but you can see there's a lot less hair in the slick animal. And these slick Holsteins regulate their body temperature better than animals that are wild type. So again, we put these eye buttons that measure body temperature into a cedar, and then measured body temperature in slick Holsteins, and then this graph up here, there's actually two graphs. One for normal Holsteins and one for daughters of slick Holsteins that did not inherit the slick mutation. So genetically, they're similar to these animals, but they didn't get the slick gene. So you can see there's a big difference in body temperature regulation. And when we look at milk yield, in wild-type Holsteins, this is milk yield during the first 90 days after calving. So it goes up, and it goes up more in the winter than it does in the summer, about a 10% drop in milk yield. But in the slick Holsteins, there's no difference in milk yield between the summer and the winter. So how long did it take us to make slick Holsteins? 30, 40 years, something like that? Before we had an animal that just had the slick mutation, but was otherwise all Holstein. Well, now we have gene editing technology. We can do what we did in the Holstein in a single generation, right? We can edit the genome of a one-cell embryo and turn the normal prolactin receptor gene into a slick prolactin gene. So that's what we did in conjunction with this company Aceligen, which makes gene-edited livestock. So we worked with Aceligen, CMEX, and used gene editing to make gene-edited Angus and gene-edited Jersey that have an alteration in the prolactin receptor to make them slick. And I know you can't really tell the difference here, but this is, both of these animals, we tried to gene edit them when they were one-cell embryos. This animal was not gene edited. This is in the summer, right? So you can see it doesn't have a lot of hair, but you can see the normal hair coat on the poll, on the face. This is a gene-edited slick animal. We shaved the hair off a piece of the flank. There's 7 times more hair on this animal than on this animal. So what are the consequences for reproduction? I don't know. But what are the consequences for body temperature regulation? I do know. The slick Angus regulate their body temperature during the day better than the wild type or non-slick Angus. And when we looked at growth rate, the body weights were heavier in the slick Angus than in the non-slick Angus. So this just shows body weight at 4 different ages, no difference in birth weight, but by 469 days of age, there's about a 50-pound difference in weight between slick bulls and non-slick bulls, and then a smaller difference in weight between slick heifers and non-slick heifers. That's pretty hard to see, actually. We also ultrasounded the animals at 435 days of age, and they had larger ribeyes in the slick animals than the non-slick animals. So this mutation has now been approved. I got to be careful how I say that. I'll say it first and then I'll change it. Now been approved by the FDA for entry of the animals into the food chain. They didn't actually approve it. They said we decline to regulate it because it's a natural mutation. So there are slick Angus bulls now that have this gene edit in them. It's not the natural slick mutation from Centipole. It's one introduced by gene editing. And Aceligen has semen from bulls that are approved for the offspring to go into the food chain. And, I think this is going to be occurring more and more in the future. It obviously depends upon how the public accepts gene editing, but this company, Aceligen, I'm working with, they now have a Holstein that they're selling in Africa with 4 gene edits, a slick gene edit, and then 3 edits that they think will increase disease resistance in East Africa. So I think we're going to see more and more of this. And, how the public will accept it, I think they'll accept it. But not everybody will agree with me on that. I do a lot of work with dairy cows. Dairy cows living in Florida are much less affected by heat stress than they used to be when I first got hired. Not because of me, but because they have really modified the environment that those cows live in to reduce the magnitude of heat stress. So there's much less opportunity to do that in a beef cattle setting, especially where they're raised out on pasture. But, there are a few things that we can do sometimes to try to minimize the magnitude of heat stress effects on the cow. And, cows are like people when it comes to heat stress. If something makes you hot, it's going to make a cow hot. If something cools you off when it's hot, it's going to cool a cow off. We're very similar. So it's not always possible, but, when we can provide shade, that's going to have a major effect on the ability of cows to regulate their body temperature. Fans and sprinklers, not a lot of use probably in a big pasture, but in the cattle pens, I've never seen fans or sprinklers in cattle pens, but it would cool cows down. And then cooling ponds. So here, by the way, is a friendly Brahmin. Right? They do have temperament problems, but not all of them. So, heat stress is some of effects of everything in the environment that acts to keep the animal from regulating its body temperature. So if we give them shade, we reduce solar radiation. Fans increase their ability to lose heat from their body by convective and evaporative cooling. Sprinklers wets their surface. When the water evaporates, the heat to drive that water off comes from their bodies. And cooling ponds, I'll show you a picture of cooling ponds, really cools cows down because they lose that body heat to the surrounding water 22 times more effectively than they do to air. So let me just show you a few pictures. This is from Puerto Rico. You can see these little Holstein heifers. Appreciate the value of shade. Shade is tremendously effective at cooling cows. Here is not such effective shade. We use a lot of shade cloth in Florida to provide cooling to cows. This is in cow pens, but the shade cloth's not very durable, so you have to maintain it for it to be effective. This is a photograph from a dairy not too far from Gainesville, Florida. These are a bunch of dry cows being fed in a fence line feeder, and they've just modified this irrigation pivot to spray a mist of water from the pivot. And if you go out there in the middle of the day, those cows are just lined up underneath this pivot, cooling themselves because of evaporative cooling from the water. Here's a cooling pond. This is on a dairy in South Florida. I've seen cooling ponds on beef cattle operations, but I couldn't find a picture of one. So these buzzards probably do not think this cooling pond is very effective at limiting these animals' response to heat stress. But their body temperatures drop tremendously when they go into water. You would think this water is full of coliform bacteria. And you would be right. It is full of coliform bacteria. But when people have looked at it, the incidence of mastitis, the incidence of metritis is no greater for cows in cooling ponds than for cows without access to cooling ponds, which I think just points out again the robustness of cattle at maintaining themselves in harsh environments. So just a few final thoughts. The magnitude of heat stress effects are going to vary a lot from herd to herd, depending on the environment that the cattle are living in, depending upon what natural protection they have from heat stress, what artificial protection is given to the cows. Water availability is going to affect the cow's ability to regulate their body temperature. They lose a lot of water due to sweating and panting when they're heat stressed. I showed some data on spring versus fall calving seasons. Obviously, there's more to spring versus fall than just heat stress, pasture availability, pricing, all sorts of things go into the decision of, what's the optimal breeding season. So one thing to consider is heat stress, but there's others as well. I think genetics is the best long-term solution to problems of heat stress. It's permanent. Once the genes are in there, they'll continue to provide protection. The problem is a lot of the breeds that are most thermal tolerant have not been selected for production like the British and continental breeds have. So we need to find a way to bring the good genes in and avoid the bad genes. I didn't talk about this, and I feel guilty about it now because there have been so many talks about reproductive technologies. How do they change the equation? So if you do artificial insemination with frozen semen that was collected from a non-heat stress bull, which probably pretty likely, you avoid all the effects of heat stress on the bull. But AI doesn't make the cow any more fertile. Makes the sperm more fertile, not the cow. If you do fixed time AI, you avoid the effects of heat stress on the bull, and you avoid the effects of heat stress on estrus detection. You don't need to worry about the fact cows aren't displaying estrus very well. But again, cow's still infertile. The oocyte is still damaged. Embryo transfer, the most expensive solution, pretty much solves the effects of heat stress on the establishment of pregnancy. We transfer embryos into cows usually at day 7 of development. So that embryo already got formed, so already from a good oocyte, a good sperm. It already developed to day 7. And by day 7, the embryo is resistant to heat stress. You're still going to get effects on the fetus later in pregnancy, but there's a lot of evidence that there's either no or very little drop in pregnancy outcomes due to heat stress for embryo technologies. So thank you very much for your attention, and thanks for the invitation to be at this meeting. I really learned a lot.
All right, thank you, Dr. Hansen. We have time for questions.
Does hair color have any effect on the heat stress?
Yes, it does. I used to be laughed at quite a bit because I was studying black cows and white cows. Light-colored hair reflects solar radiation maybe twice as much as black hair. So if cows are out in the sun, a light-colored cow is going to be more likely to regulate her body temperature. The one problem that might result, I haven't seen it personally, if they have light-colored hair and they also have light-colored skin, will they suffer sunburn more? So I haven't seen that, but I think certain kind of pastures, like clover pastures, make cows more sensitive to sunburn. So maybe a light-colored cow, in that case, might have a problem. Brahmins, put a little plug for the Brahmin, gray hair, at least gray Brahmins, and black skin. So they have like the perfect combination. They reflect the maximum amount of solar radiation, but then their skin is very resistant to any kind of damage. So yeah, it is important. How about red versus black? Not as much of a difference.
I have a question, Dr. Hansen. So what do you think would be more effective and maybe quicker thinking about selecting animals for production, right? So do you think it would be easier to find those breeds that are more heat tolerant and select them for production versus getting, those productive breeds and getting them adapted to heat stress?
Yeah, no, that's a very good question. And, if you look worldwide, people have explored those different strategies in countries like Africa, where the nutritional status is a lot lower. And so they do the opposite. They take adapted breeds and bring in productive breeds, and they usually die, even the crosses. Yeah, I think, first of all, that except for some extreme environments, in the U.S., effects of heat stress are less. I would rather select for production in the environment where the cows are living, realizing that you're probably also selecting for some thermal tolerance traits if you're in a place where heat stress is a big problem. The problem is the more AI you use, then you're using bulls who are getting genetic predictions based on the production of their calves in the whole world and not just in the environment you're living in. Are there a lot of sire by environment interactions? When I first got hired at Florida, the geneticists told me, no, there are none. The best bull in Wisconsin is the best bull in Florida. But I think that's not true. There probably are sets of genes that work better in one location than the other. So finding them is kind of tricky.
One last question.
What's the effect of the select hair gene in real cold environments? Any negative sides there?
That's a very good. So I just have anecdotal data. I don't have any data. I just have stories. There are centerpoles living in Knoxville, Tennessee. The guy who has those they do grow longer hair in the winter. It's not as long as a non-slick animal, but they do get a winter hair coat. He says they have no problems. ABS and Slick Sires produce slick Holstein bulls in Wisconsin, so they say they're fine. But of course, they're probably getting more environmental modifications than the typical animal would. It's one thing we really want to look at. When does it become deleterious to be slick? That's a good question.
All right, let's thank Dr. Hansen one more time.